Okay, how to tell it's sedimentary rock. If you want to copy this down, you have this, please copy it. Pause it now. Okay, so this have conglomerate. This is actual size. Conglomerate have pretty large sizes. They're rounded, cemented together. I wrote actual size on here. So how to tell a rock is sedimentary. That's really way, one place that I really want to get you is you will pick up rocks during your life and be able to tell, at the very least, igneous, sedimentary, metamorphic. So how can you tell a rock in your hand is sedimentary? Well, if it has pieces of other rocks and those pieces are cemented together as opposed to interlocking angular crystals, then it's sedimentary rock. A really great way to tell. If it has fossils in it, any kind of fossils, because fossils are only going to form in some kind of sediment, mud. Think about some kind of animal dying and falling into a river of lava. They're going to burn up. They're not going to be fossilized. So fossils generally form from something dying, falling down to the bottom of the ocean in mud, more mud on top, and then that becomes rock. If someone ever was to break that rock open in that exact spot, you can find a fossil. I have some pictures coming up. And rounded pieces are another key. Anything rounded usually leads to sedimentary rock. So look for those things. I have some pictures of fossils here. So this is you really can see the shells, seashells here, and if you think there's going to be a lot of fossil of marine life, sea life, especially any shells like this that are hard, because when they die, they're going to end up in the ocean. And then as long as they end up in mud, more mud on top, compacted, cemented, forms rock, and there's fossils in those rock. So that's cool. What else do I have? This is a really, really cool fossils of fish, and you really can get a sense. This is some fine mud. The fish fell down at the bottom. In this case, you can even see like its scales kind of there. You definitely see its spine. You see this spine and these bones coming out. So very cool. You really see the detail that was in its tail fin here. Very cool. And again, also important that you have to have mud deposited on top of it pretty quickly because this can't sit on the bottom of the ocean for 40 years. It's going to totally decompose, get eaten completely. So a lot of a series of events need to happen for fossils to form, which I will talk about later on in the year in a whole different unit. But not sure what Fred's doing here, but it looks awesome. I don't remember what that is. This is just some pictures of igneous, sedimentary rocks. Sedimentary rocks. There is a old guy's pipe, I'm assuming here, for scale. It's the picture that I got, but here you can see this is probably a wall of conglomerate. So, if this thing in real life is the length of a pencil, these are pretty large pebbles, cobbles maybe, size of your fist, some of them. And this tells me that this formed right near the mouth of a river where a lot of the stuff was rolling along, but not far out. It's not. It was not in 400 feet of water that's 15 miles from shore. This too kind of shows this is probably another type of. This is a pretty large sediment here. That's like a pocket knife, so maybe that's about that big for scale. This is in Resting Springs Pass, California, is where that was taken. So, some more sedimentary rock. What else do I have here? Okay. And I alluded to this. I saw that picture, showed that picture of Big Bend National Park in Texas. Sedimentary rocks form in layers called beds, also called strata. As a matter of fact, if you need to copy this, please do it now. Now, in general, when you're in class or you have a piece of rock in your hand, you cannot see the sedimentary beds in class. Okay, that's key. Any layering you see is not sedimentary beds. I meant it so much, I added an extra N to cannot. It's not a typo. Okay, it was a typo, but 3 N's, you can't see them in class. Other layering you're going to see is metamorphic rocks. But we're talking on a grander scale. When you step back and see the side of a mountain, you see the layers. That's how you tend to see this. The layers form flat on the ocean floor, and they often get tilted and bent due to plate tectonics. So they form underneath the underneath the ocean, and then they get buried, so they're pretty far down. It's plate tectonics, the plates interacting, moving together, and pushing some up. That's how it ends up being at the top of a mountain, or at least not underneath the ocean anymore. So there's usually some movement due to the plate shifting or faults that will change those rock layers. In this case here, and here's Fred again, we see flat beds of sedimentary rock, and they're labeled A, B, C, and D. Now, there's sometimes where they get lifted up and they remain pretty flat, and that happens. But really, that's more the exception. Usually, they tend to get tilted in some way, or they can get tilted dramatically, as I'm going to show you in a second. Well, actually, not yet. So this is an actual photograph. It's a black and white photograph, not great, of beds or strata. Now, I don't really have anything for scale here, but sometimes, this bed here may be about this thick, and these other ones here are sometimes they're really thin, almost look to be paper thin. So you see thicker ones, thinner ones, then this thick one there, maybe that's this thick, and they're kind of intermixed here. And this can often be, could be 300,000 years of time represented in here, which the time expanse that we talk about here is just, it's very hard to wrap your human brain around. This is a classic example. Come on, this is the Grand Canyon, and this is flat sedimentary rock layers that were uplifted like 5 million years ago. So the unique thing about the Grand Canyon, the way it looks that it does, is they were uplifted and remained pretty flat. As they were being uplifted, the Colorado River was flowing in it, and had a lot of erosional force to sort of cut the canyon. And it's this really flat sort of layer cake type of structure of the rock that makes the Grand Canyon look so beautiful. If these rocks were all tilted and folded, it wouldn't look like this. And sometimes you could see some of these layers. You can see them off in the distance. Like that's a layer there, and you can even trace them all the way along. You see these layers out here. So really dramatic when you see it like this. And these are some beds. This bed is 120 feet thick or something like that. So the Grand Canyon from here to the bottom represents, it's well over 1 billion years of time. I know the rocks at the bottom of the Grand Canyon are well over 1 billion years. Billion with a B, which is crazy. Oh, back to this picture again. I showed that before. So this is now showing tilted beds. So in this case, started out flat, then it got uplifted and tilted like this. This is a person right there, just to give you a sense of scale on this one. So the idea, thinking that's a person, this was underneath the ocean. Many other rock layers were on top, or at least sediment layers that are all gone now because they all got uplifted and it got tilted and all that stuff got eroded off over many years. And this is what we see today. And a few million years from now, this probably won't be here either, and that's all been eroded away, and we'll see the rock layers that are beneath it. Crazy. This one, I love this one. Look at this dude. Don't know who that guy is, but again, every rock layer started out flat. That's how things are going to settle out of water, always very flat. And not only was this tilted like that, this got tilted. This is tilted like 90 degrees, so there's been so much movement of the crust here because of plate tectonics. And with this guy for scale, so these are all rock layers. Now, I can't tell which way was down. Did they get tilted? Did they get tilted like this, or did they get tilted like this? I can't tell from this here. There's other ways to tell if you're there. Rarely do you see them so straight up. But it is very cool. These are some line diagrams. We talk about this more in landscapes when you have sort of uplifted sedimentary beds that are undisturbed, but they've been eroded a bit, but the layers are still pretty flat. There's a dome-like structure where it got pushed up in the middle, and there's layers here, and the road's a certain way. They could be tilted or faulted when those rock layers will break because of plate tectonics. This is called a fault. We'll learn about that later in the year as well. They can get folded. You can think of rocks bending. You don't really think about that, but it does. But they're kind of warmed. I'm going to just say kind of warm, and then that pressure on them is really, really just slow and constant. And the rocks will actually bend, and you see folds like this. So next time you're driving, if you're driving somewhere and you see those rock cuts, the road cuts on the side of the road, you can often see that the rocks are folded and all the weird structures of that. What started out like this. And it changes the way you look at those rocks. Those rocks oftentimes, I have so many people tell me, I never thought about those rocks ever, never thought about them. And now just learning a little bit about this just changes the way I look at them. I never look at them again. And it definitely brings forth a sense of awe. Or at least it should. If you're doing it right, it's going to bring a sense of awe. Okay? Next up is metamorphic rocks in the next episode.